string state of that database. Transition from any state to another state is one of the create, update, or delete operations. So basically, they provide four operations: CRUD. Amongst them, create, update, and delete changes the sequence of the database. So it modifies it. It's basically changing its state. It's is basically transitioning from one state to another state, and read doesn't cause any change because reading is like reading it. It doesn't modify the state of the database. Initial state of the machine is 5, and the current, this way the current state of the machine is the current state of the database. Let me show you an example. So it's a database state machine. Initially it's empty. Anything happens upon it initially creates 7, and anything any create, update, or delete request transitions the database from one state to another state. This definition actually helps later, but I have just introduced right now, so I will refer it later. So let's talk about current type architectures. In particular, current apps with data layers. Data layers that deal with data intensive applications. Okay. So apps with data layers generally store the data on databases in a single server or a cluster of servers, providing illusion of a single server. So this kind of apps generally actuates on the databases via application logic layer or via web APIs or directly into two-tier architectures. I will give you an example of two-tier architectures. Have you guys heard of MS Access? It actually directly connects to the database and actuates upon it. I will show you a three-tier app architecture. So this is something you guys may be familiar with. This is a three-tier app architecture where there is 3 layers of application. Basically, there is a client, application server, and database server. Database server basically handles the database requests, and application server actually has the application logic on top of it, and desktop are the users basically. So let's talk about it. So there are many problems in this kind of architecture. So I'm gonna talk about the one particular problem that's related to data layers. So data layer is the most important layer in this kind of architectures, which can be compromised in many ways, like SQL injections via UI layer or abuse of authority. The person who operates on the database, like the persons who manage the database or who maintains the database, tampers with the database state. It's the worst case scenario. And this kind of problems arises due to singularity of the database instance and singularity of the authority. And in case of SQL injection, lack of continuous database of the continuous backup of the database instance. So how to solve these problems? So singularity, it's easy. Multiply the database instance copies, share the hosting of each copy, and authority. Via multiple hosting of the copies, this problem automatically gets solved by itself. Let's talk about backup. Backing up the database continuously, it's not a good option because some databases might be huge in size, like in terabytes, so it can generate a huge data fingerprint. So instead, we preserve the transitions or the change requests which it received, and we could dynamically store them. So it becomes easy actually. So current three-tier architectures look something like this. There is this web form which serves the UI of the application, and there is this application logic layer API form which actuates upon the central database, what previously looked like. And now if we introduce multiple copies of the single database, it looks something like this. There may or may not be this API layer on top of it. So we will talk about this layer after later. So actually, by multiplying the copies, we expose ourselves to new problems. We are going to talk about those problems one by one. So how to support change requests across multiple nodes? So we need to uh, update the database continuously in order to provide it in order to actually in order to provide a service in kind of a so it can be solved via simply communicating or propagating or broadcasting the change request received by a copy to all the copies in order to sync the same state of the database in all the copies. Also, when we are broadcasting or propagating those change requests, we can also append it to the list of the uh, previously received change requests and store on top of it. So backup also becomes easy. The question: how to make changes concurrently or in order? It might be a case where two nodes or two copies receive two change requests, two different change requests at the same time. So we need a central service to collect the requests and commit them properly later. How to securely maintain change requests backup across multiple nodes. So currently we are storing them in a list, like kind of appending the orders, appending the transactions or transitions or change requests which received and appending it at the end of the list. So before that, I would like to show what's hashing. Hashing is basically mapping from one string space to another string space. So here I shown an example. There is SHA-256 of string ABC. It's basically this long string. And also SHA-256 an irreversible function or irreversible mapping. So what we are currently doing is storing the request received continuously and appending at the end of the list or change request list. And what should we do? This is what should we do in order to keep them securely. So as there is this new thing init hash or block hash, should I say, or previous block hash. So this is initial blocks, that's why init hash, and it's block 0. When the new block is received, the hash of this whole block, it's basically a binary sequence or a string in a very vague way. So we can hash it into and put that hash into this new block's header. So what happens? What happens when we store this? Store the hash of the hash of the previous block like this. It kind of generates immutability among of the list. So how is it immutable? So let's say I want to tamper with request number 7, and this is old chain, or let's say there is 30 blockchain, or let's say 300 blockchain. So if I change a single bit in this request, so this a single bit in this request actually changes hash of this block, and so hash of this block actually is stored on this block, and so it actually generates an avalanche of the changes. So I need to actually recompile the whole chain from that block which I want to change. And this is one of the reason blockchain is actually called a blockchain. There are two more questions. Which copies to trust when making changes, and how to check if a result is legit or resulting to a state that it's supposed to. These two questions actually reduce to whether a decision problem, basically, whether or not a block with a bunch of requests should be committed to the database and added to the blockchain on each copy. We have multiple copies. What we can simply do is we can distribute the block and endorse that, or basically simulate those changes on top of these those databases, and see if majority of the nodes result into the same state or not. That's called a consensus algorithm. That has to be do with something to do with consensus algorithm. This is actually practical Byzantine fault tolerant consensus algorithm. So we will talk about that later at the end of the presentation. So how can we check if the result into the same state? We can't compare the whole copies, obviously. Well, we don't need to. We only need to, and we can easily compare the changes the requests made, and that's easily possible actually. So there are these definitions. What's a consensus algorithm? So it's an algorithm designed to reach on an agreement upon a decision among multiple parties, in this case multiple nodes. So there is this some famous consensus algorithms and some blockchain platforms in which they are used. This is PBFT, Practical Byzantine Fault Tolerance. It's used in Hyperledger, Stellar, and Ripple blockchains. Proof of stake, it's used in Ethereum 2.0. Proof of work, Bitcoin you might be familiar with, and Ethereum before Ethereum 2.0 or previous versions of Ethereum 2.0, less than 2.0 actually. They used proof of work as a consensus algorithm. So this is PBFT simulation on a Fabric network. So here you can see there are two databases actually holding the holding two copies right here. This is CouchDB0 and CouchDB1. CouchDB is kind of similar to a MongoDB interface, except it stores the data in key value pairs, not in JSON format, but in actual and key value pairs. Mongo stores the data in a list of the JSON objects. CouchDB stores them as key value pairs. So let me show you the simulation. So there is this client and two APIs built on top of two peers. Peers are basically supposed to maintain the request on top of the CouchDB, and it also simulates the change request which came from the clients. This order is actually orders the change request on top of peers. So this endpoint is API endpoint is activated, and it grabs some certificates from the certificate authority. Then it distributes the change request to peers of particular organization. Fabric. One thing about Fabric is a multi-organization architecture. It enforces multi-organization architecture in its software. So these two peers are endorsing the transaction right now. When endorsement are received back to the peer, the API converts it into a transaction and sends it to the ordering service, and orders them to the peers, and at the end the peers commit those transactions, and the information travels back. this is the particular scenario of Fabric, Hyperledger Fabric. So what's a blockchain? From the previous discussion, it's a single instance, multi-copy, highly secure database. It's nothing but a database. What's a transaction? In the language of blockchain, a transaction is basically I previously showed you the database state machine. Any transition is a transaction in there, or any change request which came to a database is basically a transaction. So a read request is not a transaction because it does not cause any change on top of the database. So what's a chain code or a contract? So you guys might have heard these two terms in blockchain or not. So it has to do with a simple question. What if we store the application logic layer in the blockchain itself? So I'm going to actually introduce you to the contract later in a hands-on session. So what's a private blockchain? Private blockchain is a blockchain which isn't accessible to all, like Fabric or Ethereum in a isolated network or a private network. What's a permission blockchain? Blockchain basically which provides API to implement authorization in the contract is permission blockchain or certificate via certificates. So Fabric provides it, and it's a permission blockchain basically. So let's talk about performance. Performance obviously gets down due to the network bottleneck and what should I say? And existence of multiple instances. That's why. So there is Bitcoin. Bitcoin it provides 4.6 transactions per second. Ethereum 15 on an average. Ripple network provides 1.7 into 10 raised to 3, 1700 transactions per second. It's minimum what it provides on an average. Fabric provides 20,000 transactions per second. EOS is it's very high performance blockchain. It provides 50,000 transactions per second. There is one more thing. I actually told that before. Read request is not counted as a transaction. So read request can actually be submitted to any of the copies, and it will result to the same answer or same response from any of the copy. So why should we use blockchain? So it has to do with security, decentralization. It's backed up all the time, and it's high availability. So it provides more security due to its distributed hosting of the database. Decentralization, it provides decentralization of the database hosting and hence the authority. So a single authority can could tamper with the database state in a previous model of the database. Now they cannot actually. It's backed up all the time as I showed you. It's basically maintaining the change request in a long list in form of blockchain, and it's highly available. Due to multiple instances, it's actually one of the instance goes down, other instances are still available. So that provides high availability. So let's see it in action. We are going to actually do a hands-on. We are going to use Ethereum blockchain. It's just a blockchain service to simulate Ethereum network or to simulate development Ethereum network, we are going to use Ganache. To talk with it, there is this third party library, or actually Ethereum library. Uh, it's uh, it's API on top of the Ethereum network. It's called Web3. There is this third party wallet or plugin, MetaMask. It basically preserves your credentials in its secure wallet. By credentials, I mean your public key and private key in case of Ethereum. And there is this site remix.ethereum.io. It's basically contract development tool. I'm going to show you. What we are going to do, it's basically, as I showed you earlier, this is what blockchain looks like, or multiple instances of database looks like. So for development purposes, we can replace that with Ganache over here, and MetaMask with your Chrome to secure your credentials. Also, one more thing I should tell you about, MetaMask injects a Web3 class instance into the page, into each page actually, if it is installed in the browser itself. So as I told before, Web3 is just Ethereum API, application programming interface. So you guys have any questions till now? Do you have any questions?
So I'm just asked a question in the chat.
Okay. How do you decide which nodes to endorse? It's actually, in case of Fabric, let me talk a particular scenario. In case of Fabric, the organization consortium is basically a group of organizations. They decide the same, their operational authorities decide themselves which node is going to endorse a transaction and which node is not. There can be only node there also can be nodes which does not endorse a transaction, which basically commits the transactions directly. It does not endorse them. Okay. Anyone else? Okay, so let's start. Here is that site I told you about. I was practicing it before. So it's basically a contract development tool. It helps you test its functionality and other things. It provides Solidity programming environment here. Ethereum contracts are written in Solidity language. So we are going to create a basic example, basic contract, e-approval contract, or let's say let me discuss with you a use case. There is this government organization. If we want to create a new, if we want to start a new business, we need to get government's approval basically. So in the current systems, it's actually this kind of requests are stored in central database and it's operated upon it. So let's try to decentralize them. So we are keeping four basic functions in mind, and those are to create a request and store it, to retrieve stored request from the database, to approve or decline a request. So let's start. Solid. This kind of programming actually is very similar to object-oriented programming. There is this constructor, and we need to provide its visibility. This owner. This is basically a public key of an individual. So whichever deploys is called its owner. There is no particular use case of this line. For now. Okay. So let's start with one of the functionalities to create request and store it. So function. It should have request description. And it's public. So before we do this, we need to actually define request structure over here. So I've thought of it of a request which has 4 parameters like assign integer ID, its ID, then sender, description, and status. Basically, I'm keeping scenarios in mind, 3 states of the request in mind, which is 0 indicates still pending, and indicates it's declined, and 2 indicates it's approved. Okay. So let's start. Let's create an instance of request. And assign its variables. We need to also do one more thing. We need to declare an array of requests in order to store it. I'm saying ID to the particular request dot length, and whoever called this function is basically going to be the request sender. And the initial status is going to be 0. It's going to be pending by default. And we want to also test this function. Also, let's write the get request function to retrieve all the stored requests. So view is used for to indicate that this function does not make any changes in the database state, and we need to also specify what it returns or type of what it returns. It returns an array of the requests and stored in memory. I forgot here to do one more thing. Push it into the request. Okay, so let's directly return request here. Okay, so let's test this functionalities first. So Remix actually provides a JavaScript virtual machine to test it out, and we are going to deploy it on a particular account on a particular chain. Sorry, not chain. Yes. You can hear me now. There is this noise. Okay, thank you so much. So we are going to deploy, and it shows deployed contracts over here. Surprisingly, it does not show any particular function. Okay. Yeah. Okay, so we are going to create a request for a chemical factory. So in the logs, it's actually the transaction is done. You can see here the request is stored in this this request array, and basically the whole array is written here. We can also create a new request here for plastic factory. Yeah, so it's basically working. These two functions are currently working. Okay, so let's build the other two functions. The other two functions are to approve and decline a request. So they are going to be easy. What we need is ID of that request. And it's public. So request of that particular ID. And status is going to be for role so here defined. And for decline request, going to be one. There are similar functions. So why did I use status is integer here? So Solidity is still in its development phase, and it does not actually have a library, or it does not provide a functionality to compare the strings. There might be third-party libraries available. So in Solidity, you cannot do like this. So this basically will throw an error. So that's why I have used numbers. For numbers, we can do that. Okay. So let's deploy another instance and create a request. And get the request right now. as you can see, it has its status as 0. So basically, it's pending right now. Status 0 implies it's pending, and it actually returns the request in an order. So there is this ID of it, then the sender address. This is the whole sender address. Then this is the description of that. This description provided by the sender, and this is the status of the request. So let me try to approve this. So yes, that's, yeah. So as you can see, its status changes to 2 implies the approve request function is working correctly, and decline request. Yeah. So decline request is also working fine. So let's deploy it on top of a test blockchain. So I'm going to start up Ganache. There is this workspace I created before. I'm going to start with a new one. Okay, so we are going to use this particular address or public account. So I'm going to import an account into this. This is basically MetaMask. MetaMask is a wallet. It securely stores your credentials of the blockchain network in it, in particular Ethereum network. It also provides support for more networks. So I'm going to add another account. Here it is, import account. So we can import an account by directly giving your private key here. So here it shows a private key. Here is its private key. I'm going to copy it and provide it over here and import. So we have by default 100 Ethereum. It's a test network. Okay, and also we can directly deploy the contract from the remix itself. So what we need to do, we need to go into this run tab and choose environment as Web3 provider as its environment, and Web3 provider is at the endpoint. Here I think you can see this localhost 7545. Yes. Kaustubh?
हेलो
Yes.
अच्छा एक गलती से हो गया माइक का
Oh, it's okay.
Sorry.
So it provides its endpoint is 7545. So I'm going to do that. 7545 and connect to it directly. So all these accounts are currently unlocked. So it's basically open for transactions directly. It's a test network. It provides those kind of facilities for now. And I'm going to deploy a network a contract here. So it's basically deployed. So what we are going to do, we are going to provide a web interface on top of this network. So I'm going to copy the contract address from here and start with the project. So it requires it requires this Web3 library. So it's basically application programming interface on top of the Ethereum network. So let's start with this index.html and index.js. Okay. You guys can see the code now. This is something new. This is called contact API. So we are going to extract it from over here. This whole string is called contract API. It's used to interface with the contract itself on the network. So we are going to need it later. Actually, I have reserved it for now. So let's start with the init function. And how it's working. And let's connect the interface. So we need to import that script into the page. So next.js. Okay. So let's see if it's working or not. So I'm going to start a live server here. So it basically serves this index.html on top of a server. And the developer panel. So you can see here it prompts working, and so basically the current binding is working for now. So before we start anything, we need to connect MetaMask. We need to connect the MetaMask to the page in order to actuate on the network, or in order to uh, uh, order some transactions from the account. So I also need to record that MetaMask injects a Web3 instance into the page itself. So it's already a Web3 instance. It implies that MetaMask is already present there, and it's actually okay. It's okay. Or else we could return false. We're going to need it over here actually. So it stops execution if MetaMask is not installed. And we're also going to indicate is installed. So now what we're going to do, we're going to ask for connecting a permission from MetaMask. Before we do this, it's actually injecting a newer Web3 version into the page. What MetaMask does is it actually injects a previous version of Web3. So we are going to actually inject the newer version of Web3 into the page. So it replaces the older version of Web3 from here. Before we do this, we need to actually import the library Web3 into the page. So I've already downloaded it from the source. I'm going to leave it in the description. And to make things easier, I have also downloaded jQuery to actuate upon the page from the JavaScript itself. jQuery, okay. So jQuery. basically a provider which it's another instance that MetaMask injects into the page, and we are going to request that that instance to allow MetaMask to be connected with the page. Ethereum dot and then return true. Okay, it's basically not asking for my permission because I have already okay, it's working for now. We can console.log it. So here we can see a JSON object. So let's interface to interact with the contract itself. So I'm going to declare a global variable here. And we are going to need defined variables here. Contract API, we need to pass in contract API and then contract address. Right over here. Okay. So what we're going to do, we're going to retrieve all the invoke this get request function, and we are going to read the stored request for now, which is going to be none. So we have not created any requests yet. So we can do that by and dot call. This is the method written over here. So let's call back. Yeah, it's working for now. So it does not it provides an empty array because we have not created any requests yet. So let's go and create some requests. So okay, function to create a request. Okay, we need to get some fields here. And ID. And return. And one click function. So we are going to receive the this function is basically going to be called when this particular button is clicked. So let's retrieve the content of this text box from here. Description is going to be, so I'm going to use tick here to select this text field from the page and retrieve its value. Description from over here and dot value, and then call them invoke the contract method from here. Description as parameter and send it to the network. To send directly these 4 parameters to be passed with this particular function. So it ends from, so 50 dot so the currently selected address in MetaMask itself, which is going to be this account 508342, this one. So we are sending the transaction to the contract, so contract address and amount for the gas. So let me choose some random values here. This is basically incentive for a miner. I have not used that word before, but it's basically incentive for the miner to mine these transactions into the Ethereum blockchain. So there is no miner right here because it's a test network, but we need to provide it. So I'm going to provide some really weird values here. It's actually in G ways, so it's a smallest unit of Ethereum, and it's basically returns the promise. So .10 we need to provide a callback. So it will generate a transaction else after sending it to the network, and we are going to do a console.log here. And if any error occurs, we are going to directly log it. Okay. So let's try and create something. This problem. Create property selected address of undefined. Acha, okay. Yeah, so this window pops up. Just a second, I need to change the account. Okay, there is no connected site here. So there seems to be some problem over here. there seems to be some problem. I'm going to quickly look to my previous code. Okay, it seems to be the same. It's the same. Okay, now it's connected. Sorry for the delay. Okay, so yeah, it's confirmed. So from this line where we are currently logging all the requests. So here, as we can see, there we created a request and it's received here. So let's try to show it in a table form. We have to create a table. So we have 4 fields. This is ID, description, ID, sender, description, and status. We also need ID table. So request table. Okay. Okay, so on the received request, added to each request. And we need to actually add the table from the page in jQuery instance. Okay, this will get the table from the page, and let's insert a table row into it. So this will create a new table row. Okay, and insert into the table, table.append. Okay, and before that, we need to actually insert the table data into the table row itself. So request dot for each. We have this array of 4. So for each attribute, here dot append new TD object. jQuery and attribute. Okay, so it should be now. Why is it not working? Oh, yeah. Okay, So we got one request here. Okay, let's create another one. Okay, it's confirmed. I'm sending way too much gas here. Okay, also let's add auto refresh code after creating the request. Okay, so let's also add approve and decline request functionality. To request, we are not going to need that, but we need ID. So I have actually here parameterized the ID because we are going to need it over here. Everything else remains the same. Okay, so we need to insert two more buttons into the into a particular table row. So what we are going to do is define to form a button and receive it. So we are going to need three parameters: value, ID, and on click function. Okay, that button is basically input type. Its value is going to be 12. Okay, and we are going to attach an event listener. Something will be called when this. So we have already received on click function, and that particular row ID or request ID, we are going to call that function, and return that button. Okay. Now directly append get button to ID is where it is basically a zeroth object of this array, request array. So request and 0, and on click function we are going to pass this function we just created, approve request. Okay, so there is also going to be decline. We need to create a decline function. So it's going to be exactly the same. Decline request. Okay. Selected address. Yeah, everything is fine. Decline request. Okay. Yeah. These are the buttons. So let's try and approve one. Okay. So as you can see, we have here status as status code 2 implies this request is successfully approved. So that's what I prepared for today. If you have questions, please ask. guys.
So I guess there are no questions over here. What we can do is we can share the code with you if you want to have a look at it and see what's going around.
Yeah. Okay. So I'm going to actually commit the code. So let's add the contract itself. So I'm going to copy this whole contract, paste it over here. So this is the site base code right here. It's just remove .git from the end. Let me do it. Yeah, it works. Okay. Yeah. So I'm gonna share one link. So if you're interested in learning Solidity to create this more complex contracts, you can go there and learn Solidity language from there.
Yeah, I guess if no one has any questions, we can end this over here. Okay, cool. Thank you all for coming.